Vipi? Sasa amepewa risiti kabla hajalipa.
All right. Good morning again, everyone. Glad to have you here. Thank you for participating. Hope you're all doing very well today. The topic for today is oil breakdown voltage, or BDV, as it relates to the process of working with power transformers. And in today's webinar, we will discuss the following things. The standards for determining the breakdown voltage, how breakdown occurs in the transformer. We will talk about how to collect samples of oil properly and which factors influence the breakdown voltage. We'll also touch on what the oil breakdown voltage test actually shows and how we interpret the results. And we'll talk about technology for measuring the breakdown voltage in online mode or in the field during the purification of transformer oil. As you all know, anyone can participate in our webinars. The participation is entirely free. It does require prior registration. So if you have a friend who is interested in these topics, let them know, because we have these webinars regularly and they might be interested in joining us in these events. All right. Also, just a quick reminder, if you do require sort of a certificate of participation in these webinars, please contact the manager who invited you in GlobeCore, and you can get that. Also, you might have questions in the course of the presentation. What we've done before and what we're going to do today too is we're not going to interrupt this to answer questions, but you can ask these questions in the text chat, and all of these questions will be answered either during the presentation, or if we run out of time, somebody will get back to you with an answer to that question later on. Right? Okay, with that out of the way, let's go to the subject of these presentations. So we should all know that prevention is much cheaper than correction. The monitoring of transformer condition and its liquid insulation, well, it makes it possible to diagnose problems related to both the oil and the transformer. And this allows us to repair the equipment and take measures before it fails dangerously, which can cause severe damage to your facilities and large losses for your company. So the breakdown voltage is a very important factor or indicator of the quality of transformer oil. And what it does, it characterizes the ability of the liquid dielectric to withstand an electrical voltage without suffering a breakdown in its dielectric or insulating properties. And that is, it defines operation without problems of the entire insulation system of the transformer. So the breakdown voltage test, it is a test that aims to define the average value at which an insulating fluid allows an electric arc through it. This is achieved by increasing the voltage to which a fluid sample is subjected gradually until a spark occurs. And it's because of this spark that in many places this test is known as a spark test, and the equipment is also often called a spark meter. Next slide, please. Contamination of oil dramatically reduces the breakdown voltage and can make the oil unsuitable for use in transformers. And therefore, the breakdown voltage test is useful to determine the degree of contamination of the dielectric oil. But the test does not actually show us what the contaminating element is. So a low value in this test should be a warning, and it should be followed up by other tests. And those tests will define what is actually causing the low value of the breakdown voltage. And additional tests are the key to determining which specific material, a substance, is causing the loss of the oil's dielectric strength. Next slide, please. Okay, so with that, we have some theories that explain to us and help us understand why breakdowns actually occur. So there is the thermal theory that explains breakdown due to the appearance of a gas channel as a result of the boiling of the dielectric itself in places of local field heterogeneity, such as air bubbles, etc., and they may cause the breakdown. There is the gas theory that explains the presence of gas bubbles absorbed on the electrodes of this or dissolved in the oil that lead to decomposition or leads to the breakdown of the dielectric fluid. And the chemical theory explains that the decomposition itself occurs as a result of chemical reactions that run in the dielectric oil when exposed to an electrical charge in the presence of gas. So moisture, next slide, please. Thank you. So moisture in the oil can come from many sources, and moisture doesn't even need to enter the transformer from the outside, as there are actually internal processes that cause formation of water. Leak points are the main factor responsible for the increase in humidity in the transformer. However, there are also transformers with breathing transformers, and those breathers tend to be a kind of a weak point if due care is not taken in their maintenance. So a timely change of silica gel and continuous monitoring of moisture levels, as well as alternative moisture extraction equipment, are all important to keep moisture levels low in the transformer oil. The aging of oil and paper can also result in the formation of water. The presence of particles in the transformer oil must always be reduced to a minimum, even though particle count is not a normal routine test. However, there are many measurements that determine the presence of specific particles, such as the Furan test, there's gas chromatography test, dissolved metal test, and a few others. Next slide, please. So moisture, as we know, conducts electricity and therefore obviously reduces the dielectric strength of the oil. Oxidation by products such as acids also causes conductivity by the process of dissociation. In addition, acids influence the surface of the oil, reducing the surface tension, and they therefore promote formation of bubbles, and that also influences the dielectric strength. Pressure is a factor in the formation of bubbles. With an increase in pressure, the breakdown voltage should also increase. But for pressures below normal atmospheric pressure, the breakdown voltage must be reduced. Particles will move in areas of high voltage depending on their permittivity in relation to that of the oil. So a decrease in breakdown voltage is expected if they're highly conductive or humid. So there is also, this is the influence of humidity and acidity. And in a bit, we're going to talk about the measuring equipment. Next slide, please. Okay. Studies conducted by the company Vaisala show that the presence of moisture directly affects breakdown voltage, especially shown by the ASTM D877 and IEC 60156 tests. The ASTM D877 standard has proven to be a bit less sensitive to this condition. As we can see, the breakdown voltage, when the humidity saturation is relatively low, remains at good values close to 100% of the capacity. However, when the humidity saturation values exceed 20%, breakdown voltage is seriously reduced, falling to 30%, where you can see humidity saturations of 50% and above. It's common to find high values of moisture saturation in the transformer oil. This humidity, due to its characteristics, cannot be detected with the naked eye, and it is conditioned by the oil temperature. Next slide, please. The transformer is usually thought of or described as a static electrical machine, stationary electrical machine. But in reality, there is a dynamic that involves certain kinds of motion, making a transformer subject to internal changes and pressures that can affect different parts of the device. So transformer vibrations are related to the current and voltage and load on the transformer. Changes in the temperature of the equipment also produce thermal expansion and contraction of some parts of the equipment, among other processes, and that can cause formation of solid particulate matter suspended in the oil. The aging or degradation of the paper insulation also generates furans. Problems like excessive heating or local hotspots generate suspended solid particles, and the degradation of oil allows the beginning of a coagulation process where small particles clamp together and form larger particles, and that may even result in sludge later on. Next slide, please. Okay, so there are also gases in the transformer. They are the result of separation of hydrogen and carbon atoms from the oil molecules. As we know, oil is a hydrocarbon, and that means that its composition is mainly made up of carbon atoms and hydrogen atoms. And when these molecules are subjected to high energy, these atoms can break off from this molecular chain and form new compounds. All compounds generated by these processes seriously affect the breakdown voltage. Now, the compounds that are generated and remain in gaseous form will form bubbles, and the compounds, some of the compounds that are formed by aging of oil will find an oxygen atom, and that will allow them to generate OH groups in the formation of new materials. And that gives rise to compounds such as acids and ketones and aldehydes. And a common characteristic of all of these compounds is that they are highly damaging to the transformer, in addition to being polar and facilitating the flow of electrical charge, and that directly affects the breakdown voltage of the transformer oil. Next slide, please. All right. So, like in all transformer testing, there are standards here as well that guides us, and they are what allow us to define whether a certain value is acceptable or not. The tests are also the rules that tell us what the proper procedure to perform a specific test is. These standards also define the scope of the tests that we should use. It's common for transformer oil tests to be used interchangeably, but there are characteristics that define the ideal context for the application of each specific one. All breakdown voltage measurement methods have in common the fact that they report a voltage value at which an electrical arc occurs in an insulating fluid. But the shapes of the electrodes we use can cause the test to vary in their focus. For example, ASTM D877 is a test that is recommended for new oils, although it's quite normal and usual for different laboratories around the world to still continue to use it to diagnose energized operating transformers. Next slide, please. The best known standards in the world are the ASTM standard and the ISC standard. That is derived from a large number of different standards that focus on different specific markets. Next. So a very important factor that can really affect the results of excuse me, a breakdown voltage test is the quality of the sample collected from the transformer. A poorly collected and a contaminated sample can distort the results of the test. So it's very important that we take the following steps during the sampling process. So when we take a sample, we must record the identification of the container on the label. We should write down the date and temperature of the sample at the time of collection. Before starting the test, the sample must be inspected visually for moisture, sludge, suspended particles, or any other foreign bodies. And if the sample shows any evidence of free water in it, the breakdown voltage test should not be performed on that sample, and the sample must be reported as unsatisfactory and discarded. Next, please. So continue with the characteristics of the different methods. This method that we're talking about now is ASTM 877. It's actually the oldest standard. It's not very sensitive to the presence of moisture, and it's actually more suitable for analysis of new oil that you may receive from the manufacturer or something similar. Next slide, please. So Here you can see how ASTM D877 treats acceptable values for the oil. You can see that anything acceptable is breakdown voltage above 30 kilovolts. Anything that falls in the range between 30 and 25 kilovolts is questionable, may require further attention. And anything below 25 kilovolts is unacceptable, as such oil must not be used in the transformer. Next, please. So an interesting question that may arise now is when we should use the ASTM D877 method. So this specific method is most widely used for the evaluation of new dielectric oils received from the supplier. Excuse me. However, this method is not recommended for insulating liquids after they're put in use or commission, which means that it's not recommended for transformers that are already in service. Next slide, please. All right, talking about the electrodes that are used in the text, the surfaces of the electrodes must be parallel, the faces of them. The axes must be coaxial, coincident horizontally when they're mounted in the measuring cell. The polished brass electrodes are constructed as discs, 25.4 millimeters in diameter, that's 1 inch. And they should be at least 3.18 millimeter thick. That's 1/8 of an inch. They should be thick with sharp angled edges. The sharp edge must have a quarter circle radius no greater than 0.254 millimeters, basically 1/100th of an inch. And in the standard, you can look up Annex A1, where you will find illustrations of edge radius measurement. Next slide, please. Once again, the edges of electrodes must be sharp. Rounded edges will generate higher breakdown voltage values. That will cause, if we have like unacceptable oil, unacceptably bad oil, it will show acceptable BDV values. So you can generate high values in degraded oils, which could confuse us, and it could cause us to accept a bad oil for use that should actually not be used. And the cleaning of the electrodes is also very important. The electrodes must not have any corrosion on them because corrosion can generate falsely low values. Next slide, please. Okay, let's look at another method, the ASTM D1816. The 1816 standard, although generally accepted as a bit more useful probably than the D877, has an important limitation. When testing oils in service, this method is very sensitive to dissolved gases. So if we have excessive amounts of gases in the oil, they can decrease the test results significantly to the point that an oil sample might be generally adequate and acceptable with low moisture and low particle count, but it can still fail the test, which is also a false result. That must be taken into account. Next slide, please. So the electrodes in the standard are made of bronze as well, must be polished, must be free from any pitching, scratches, any corrosion or any deposits of carbon or something like that. And the oil during the sequence of the test must be stirred. Usually it's a 2-vane motorized impeller. The standard prescribes the impeller dimensions and the pitch of the blades, as well as the operating speed, which must be something between 200 and 300 RPM. And it's very important to prevent air from coming into much contact with the tested oil. So the test cell that we have our sample in must have a cover or a deflector of some sort. Next slide, please. So first, what we do is obtain a sample of the insulating liquid to be analyzed using an appropriate ASTM approved sampling device. The procedure for sampling the insulating liquid is detailed in practice D923. Special attention should be made to the general precautions in the test method. The sample must be protected from light until it's ready to be tested. Plastic bottles are not particularly good for this purpose because they are permeable and the amount of moisture in the sample can change. That results in a measurable difference when comparing samples collected in non-permeable containers. And before starting the test, the sample must be inspected again visually for the presence of moisture, any sludge, particles of metal, any other foreign bodies, etc. So if the sample shows evidence of free water in it, that BDV test should not be performed. The test should be discarded. The sample should be reported as unsatisfactory, and the sampling procedure repeated. Next slide, please. On this next slide, we can see the acceptable limits as described in the D877 standard, which uses two types of spacing on its electrodes, specifies two types of gap between the electrode. The first goes for a distance of 1 millimeter between the electrodes, and the second talks about a distance between the electrodes of 2 millimeters. And we have acceptable breakdown voltage values depending on the voltage class of the transformers, and this is shown in this table. With a distance between the electrodes of 1 millimeter, we have acceptable breakdown voltage values of 23 kilovolts, then 28 kilovolts, and 30 kilovolts, depending on the actual voltage class of the transformers. So as we see in the first column of the table, with a distance of 2 millimeters between the electrodes, there are the following values, according again to the voltage class of the transformers. First, we have 40 kilovolt, then there is 47 kilovolt, and then finally 50 kilovolt. Next slide, please. Okay, another important and very interesting standard is the IEC 6156 standard. It's the European standard for breakdown voltage testing. Many test patterns are based on this standard and this method. And the most notable feature of the standard is the use of spherical type electrodes. Next slide, please. So in this test, the volume of the cell must be between 350 and 600 milliliters. And the cell itself must be made of electrically insulating materials. And the materials must not be hygroscopic. So the cell should be transparent and chemically inert, resistant to the insulating oil itself and to any cleaning agents or detergents that can be used to wash it. Glass is actually the preferred option for that. So the cell must be provided with a cover. As I've mentioned, oil must be prevented from as much as possible from contact with air. So the cell should be covered. It must be designed so as to allow easy removal or dismantling of the electrodes for cleaning and maintenance. To improve the homogenization of the tested sample, a rounded bottom cell shape is recommended. Containers and the lids of the containers must be washed with a suitable solvent or by clean oil to remove any residue left over from previous sample. And after cleaning, containers should be closed tightly and immediately and kept closed all the way until their use. And the electrodes that we have, the removable electrodes, must be stored in clean insulating liquids for protection. Next slide, please. So the electrodes must be made of brass, bronze, or austenitic stainless steel. They must be polished and spherical in shape. We're looking at diameters of 12.5 to 13 millimeters, as is shown in figure 1 of the standard, or hemispherical with radiuses of 25 millimeter plus or minus 0.25 millimeter. And that is shown also in the standard, in the figures in the standard. The axis of the electrode system must be horizontal, and the axis of the electrodes must be at least 40 millimeters below the sample surface. Now, regarding an agitator, the use of an automatic stirring device is highly recommended to be used at all times during the test. Such device should be mounted on the test cell to maximize the homogenization of the liquid sample. It must be designed in such a way that it can be easily cleaned. Stirring must be performed by a two-blade or another appropriate agitator or impeller with an effective diameter anywhere from 25 to 35 millimeters, with actual depth of 5 to 10 millimeters, and it should rotate at about 200 to 300 RPM. It's important that the agitator vanes don't produce bubbles of air in the oil, so it must be completely submerged in the sample. Next slide, please. So the first application of voltage should begin approximately 5 minutes after the cell's filled up. And we should see that there is no air bubbles visible in the electrode, between the electrodes. Then voltage is applied to electrodes, and it's uniformly and gradually increased from 0 at a rate of 2 kilovolts per second, plus or minus 0.2 kilovolts, until the breakdown, the fault, or the arc spark occurs. The test requires 6 runs on the same cell, allowing a pause of at least 2 minutes after each arc before reapplying the voltage. Again, check always that there are no gas bubbles in the gap between the electrodes. If the insulating liquid nominal viscosity is greater than 15 millimeters squared per second at 40 degrees, then the hold time before applying the voltage, before starting the test, should be increased somewhere from 15 minutes to 30 minutes. And if that is the case, we also need to increase the hold time between 2 consecutive shots accordingly. Next slide, please. So the first values that you can see here are typical for transformer in use. And the second table shows the values acceptable by the standards for new oil. Okay, so a quick comparison here of the BDV test patterns and methods is presented here. We can see the characteristics of, or the rate of voltage increase, the shape of electrodes, the amount of oil needed to perform the procedure, and suggested times for sample mixing and hold times. It can be seen from this table that the ASTM D877 standard specifies increase rate of 3 kilovolts per second, and the IEC 6157 standard specifies an increase of 2 kilovolts, while ASTM D1816 standard gives us an increase of slow, gradual increase of just 0.5 kilovolt per second. And another important element here is the distance between the electrodes. As you can see, the ASTM D1816 standard presents 2 alternatives for this distance. This means that this should be taken into consideration in analysis of the result. We must know what was the distance between the electrodes when we interpret the results of the test. The adjustment of distance between the electrodes are made with special distance measurements determined by the standards. It's essential that when we do this test, that the distance between the electrodes is precise and is measured and adjusted correctly. Next slide, please. Okay, so the improvement of the dielectric strength value, which is what is important here, depends entirely on the element that causes the problem. That is, when there is water, a thermal vacuum process will remove water from that oil. And you can see there is a certain dynamic to the process. When we first start the process, there will be a sharp rise in the breakdown voltage. Then breakdown voltage increase kind of slows and stops and hangs at around 60 kilovolts. At this stage, we've removed any emulsified free water, and what we start doing is removing dissolved water from the oil. And from that point, the breakdown voltage rises slowly, reflecting the slow removal of dissolved water. Solid particles can be removed by particle filters, obviously, such as paper or anything similar. But there are polar compounds that require some chemical or microfiltration processes to be removed, and that may include oil regeneration or using bleaching clays, etc. Next slide, please. So as it can be seen from this presentation, can be inferred that the breakdown voltage, or a BDV strength test, is a common field test that allows us to determine the progress of a transformer oil treatment process. So GlobeCore presents here the TOR-80 machine, which is a measurement system for this parameter and can be easily programmed to perform the test safely, quickly, and reliably. It is the ideal equipment for field work, where it's possible to analyze the progress and the scope of the oil treatment process, including a process of regeneration. The instrument has a pretty simple and straightforward intuitive software for control. It even allows you to configure the test pattern to your liking or according to any standards. And all of the processes in this tester do meet the high and varied standards for transformer breakdown voltage test. Next slide, please. All right, here you can see what it looks like. You can see the components of the TOR unit as manufactured by GlobeCore to measure the breakdown voltage. What you might look into is it's equipped with a printer. There is an integrated matrix printer that you can use to quickly print out a receipt-like slip of paper with the results. There are controls, several keys that allow you to change the test procedure, test the parameters, individual parameters of the test, and save that. The measuring cell itself is covered safely with interlocks for safety, just so that somebody doesn't stick their hand and get zapped. There is a USB connection port if you need that to connect that to a computer. And of course, there are handles for easy transportation of the unit. Well, relatively easy because it's kind of heavy, but you can still handle it and take it from place to place in the field where you need to use it with a transformer. Next slide, please. So here there's a big table with specifications of the TOR-80. What's important here is the equipment. This equipment can be powered by voltages from 85 to 264 volts. That means that you can plug it into any power source pretty much, which you can find in the field during the transformer treatment process when you need to take a quick measurement of the breakdown voltage. You don't always have a standard voltage there, okay? So the maximum output voltage for this test is 80 kilovolts, and that has you covered. That exceeds the values specified by all international standards. And the measuring cell has a size of 500 milliliters. Also, that covers all of the international standards that we've discussed, so that's a sufficient volume. The weight of the device is only 25 kilos. It's relatively easy to transport, so you can probably one man or two men can handle it easily and take it from place to place. Next slide, please. The TOR-80 has a pretty easy and intuitive configuration. Again, this allows the adjustment of the distance of the electrodes with special adjustment regulation wheels, and that makes this electrode gap thing adjustment fairly straightforward. All of the parts comply with what is established by the different international standards. Electrodes can be changed and selected corresponding to the standard that is being applied. And all of the components are highly resistant to oil or chemicals or anything like that. And that makes the machine a very good option for accompanying oil treatment procedures out in the field. It's just rugged and strong and can be used out in the field easily. Next slide, please. So this pretty much concludes this session today. Once again, thank you for coming and for listening to Stock. If you have any questions, please ask them in the text window so that our specialist can answer them either now or later on. And I hope you all have a great day. Thank you for coming, and I hope to see you in the future. New webinars will be announced on our website. Stay tuned. We're going to have more topics, more interesting discussions on things. So I hope to see you there. Goodbye.